Okay.
So welcome back to the Optimization in Oslo seminar. Today we are happy to welcome Lars Ruthotto from the Emory University, and he's going to talk about neural network approaches for high dimensional optimal control. So please go ahead.
Yeah, thank you, Johannes, and also thanks to Thomas for organizing this and for having me. Pretty excited to share some work with you guys that probably you know more of than we do, because I guess you guys work with Thomas or sort of at least in his sphere, and I guess everyone knows optimal control much better than I do. So what I want to try to do is to show you a few works that we've been working on toward high dimensional control and applying function approximators like neural networks to solving some I always find interesting problems, and then hopefully, we're not such a big group, so we can actually do this quite interactively. I have a few slides for things like a wish list of things someone should be doing, but there may be good projects for you guys. Anyway, yeah, so I'm in this beautiful building in Atlanta, Georgia today. Sorry, I can't be in Oslo. I love Oslo. And actually, I wanted to congratulate Thomas on getting the position there. But I should congratulate you on having Thomas there, because he's a great guy to work with. Okay, so let's jump right into it. So what I'm going to talk about is a joint effort between my group at Emory and mostly Stan Osha's group in UCLA, and also Bart van Blom-Wander is a longtime collaborator of mine in Sandia National Lab, and really grateful for some of the funding we got for this from the NSF and from the Air Force and from the DOE. And this all happened actually in 2019, so just before COVID, in an IPEM special semester. I was there for a sabbatical, started talking to Stan, and then we kicked this off. What I'm going to talk about today is a subset of the work we've been doing for the last, what is it now, 3 years. And I wanted to talk about two problems. So one is a pretty standard textbook deterministic control problem. So you have an ODE dynamics, Z is your state, U is your control, F is your dynamics. And you want to, in this case, what we are interested in is finding a policy. So a policy is a function that maps the state to the optimal action at every time, okay? So for example, you could have an objective functional here, running cost L, terminal cost G. You can go ahead to pick one particular initial state for Z and solve this problem. I would call this a local solution, because then this is a solution as a U, it's a curve U along a path from that particular initial state. But what we are after is really a function that gets you the optimal control at every state. And what we are going to use is, if you are familiar with optimal control theory, then it's probably dawning on you that there will be some relation to the value function, which we'll probably define a little bit later, and a feedback form. So if you know the value function and the feedback form, you have the policy. That's what we want to do. The second idea, and some pictures here. The second idea I want to talk about is what happens now if you add a little bit of noise to the dynamics. So a stochastic control problem, some Brownian motion, say, is added to this. Then you can write down a similar problem and actually solve it in similar ways now with the approach that I'm going to show you. So we'll first talk about deterministic and then extend it to stochastic control. And a common thread in this talk is going to be, so you want to learn a value function representation presented with a neural network. You use HJB equations to characterize the optimality condition. And the whole name of the game is to avoid optimality when the state space becomes large. And by large, we will be modest today. We'll probably mean around like 100 dimensions or so. That's about what I think we can do for today. Okay, so that's sort of the general idea of the talk. So these two ideas come handy. If you haven't seen it, a prototypical HJB equation, which is characterizing the value function. I should say the value function is a function in t and x, and it maps basically time and state to the optimal cost to go. So it's basically, you can define it as the infimum over j tx. Okay. So a property that is going to come handy for us is that the value function satisfies an HJB equations typically. So that is a PDE. If your control problem, for me, they go forward in time today. then the HJB goes backward in time, which means that at the terminal time, you know exactly the optimal cost to go is your terminal cost because you have no time to make any decision. But then you can solve it backward in time, and it's a PDE that looks quite messy because it has this Hamiltonian term in here. So we have a sup over u and then the Hamiltonian. And what we're going to assume for today is that this term here, which depends on the first and second order derivative of the value function, is going to be benign. Let's say it's a convex problem that you need to solve, and you can do this. Okay. So anyway, so phi again is this optimal cost to go, S is the state space. We're going to talk about D being in the hundreds. You can even think about D as a function space. So I'm going to comment a little bit on some work on PDE control later. So there in PDE control, your X, so state, would be a function. So you would have actually a PDE on an infinite dimensional space. Yeah, H is the Hamiltonian. G is the terminal cost. If you have the sigma equal to 0, you have a deterministic system. Otherwise, you have a stochastic system. And really, the challenges are, if you want to get phi globally, there's a curse of dimensionality. If you want to get it, so that's a forward-backward structure in this whole problem, because you need to get a phi at t, x to decide on a future action. So you need to basically, in dynamic programming, usually you can go backward in time and then you have it, but in a high dimensional space, you need to decide where to sample typically. But what we're going to leverage here is that you typically don't need to know phi everywhere. If you can find out like what are the interesting parts of the state space, then the idea is not to solve the HJB everywhere, but just limit yourself to these parts, and thereby hopefully getting away without the curse of dimensionality. I will call this a semi-global approach. I'm not going to promise you stuff we can't deliver on. I mean, there are probably some works out there that say that you can globally get the phi, but I would need some convincing. So semi-global is for us the way to go today. The general idea is you split the problem into two parts. So offline, you learn the value function. That's typically computationally costly. So think about a couple of minutes or an hour on a GPU. Probably you can now do better if you know HPC and do that. So you beat up the problem there, get the parameterization of the value function. We call it phi theta. Theta are the weights of, typically it's a neural network, but any function approximator that works in high dimension, I will take. You sample the state space using Monte Carlo. Here is important. You'll see me hammer this point later on, that we want to find out what are the important parts of the state space. And in order to decide that, we are actually going to use feedback forms and control theory. And that drive the discovery of the state space. You like, so you can think about already a few things that you saw on the slide. So you can basically use, of course, the ODE and the PDE. You can use the objective function. You can have penalty terms. So you can basically penalize the HJB equation. You can think about something like temporal differences that you can penalize, which is sort of like a characteristics of the HJB. All of these different things go, and then you train your weights. So if you are familiar with neural networks, that's a pretty straightforward recipe for solving many problems these days. For training, so I mean, since you guys are an optimization group, I would say anything goes. I mean, so we've been using stochastic approximation methods, but also sample average approximation methods typically work just fine for this. So you replace one optimization problem that is really hard, like the stochastic control problem, say, with a different one, which is training a neural network. But I think in training neural networks, we've done we've done quite some progress in the last couple of years. So that's going to be okay. What you want to look out for is that you want to avoid the curse of dimensionality. So what is a no-go is that the network size or the number of samples or the training time, anything that explodes really with respect to dimensionality is not gonna work for you. So that's going to be one thing to look out for. But once you've done this, say you can find the phi, then typically in the problems we look at, you can have a very fast way to get the optimal policy. So if you ask me what is U star at T and Z, basically it's given by this term here, which first of all, again, looks messy because it's the max of the Hamiltonian. but we made the assumption that this is going to be simple. So this can then really be done in almost real time, much faster than solving a problem. And a benefit of this could be, so say you have an application where you optimize a nice trajectory and you try to follow that trajectory, but then halfway through you get bumped off the optimal trajectory. And then, I mean, of course, your initial plan is no longer valid. You need to go back to the drawing table and solve another problem. Here, the idea is if we sort of train well and make sure we generalize, then perhaps this U star is actually going to be useful even at some unforeseen states. Okay, so that's the general idea. Should say there is some optimal control theory in the background of this. So again, the value function is just the best cost to go. There's a feedback form, and again, there's a value function. So we've pretty much seen all of these. So this is sort of the control theory part that we're going to use to find phi. That is our main mission now. Find the phi. So let's see how we can do this for the deterministic problems. Again, there's a problem from before. I'm going to do a bit of a change here. So I have a deterministic dynamics, but I assume that my initial state is drawn from some distribution. And the reason the reason I want to do this is so that I basically fill a little bit more of the state space. Because if I want to be semi-global, I need to make room for some exploration of the state space. So that's our way of doing that. And then you can think about minimizing an average cost with respect to the initial state. You can define success differently as usual in life. So you can think about a local solution, so finding the optimal trajectory for one given initial state, not really what we're interested in, but what we want to compare against, because you want to have a strong benchmark whenever you do these things. You can think about a global solution, so you want to find the optimal policy for all the states. That is going to be tough in high dimensions, because clearly you cannot do a finite element mesh in a high dimensional space. And also when you start sampling and you want to guarantee that you sample everywhere, I think that's also going to be quite hard to guarantee. So semi-global is sort of in the middle, and it wants to find a policy that's optimal in the subset of the state space that is likely to be visited. So you don't want to get the value function correct necessarily in parts that are never going to occur in real life. So that's what we want to do. Okay. There's a lot of literature. Here's just a very incomplete list, but we have more in our papers. So in local solutions, you can do this, of course, unsupervised, which means you don't need to know the value function to get it, but you can get it with very efficient methods along a trajectory. In the semi-global solution methods, there are two different sets. So one is a supervised way. So what you do is you actually solve the local problem many times. That gives you optimal trajectories, optimal value functions. And then you are using that and you fit a higher order network, higher order polynomial or neural network to those trajectories. So that's what we want to do. We want to be unsupervised in the sense that we are just learning the value function without knowing any optimal control or any optimal policies. So there are a few ways. I think very notable is Karl Kunisch has been working with a quite nice set of papers on this in recent years, which is similar to also our setup here, that you have an expected loss over some initial perturbation. Okay, and then there are different technical differences between those works, of course. So here is a training problem, just to give you an impression of what actually will happen then once you start to train this model. So we have an expected loss function. The first part here is basically our original control objective function. So L is sort of the integral. So we write the integral of the running cost as in the ODE. This is more or less this neural ODE style, if you're familiar with that line of work. We wanted to match that as closely as possible. So okay, so that's the optimal, that's the control objective for your current trajectory once you've sampled X and initialized your state from there. Then you have some penalties. So they hopefully are easy to motivate for me now that we've looked at HJB equations. So you have this first term, CHJ. What that is, it basically is an L1 penalty on the violation of the HJB equation along that trajectory. Sorry. And the beta 2 is sort of a constraint. I think I said that you know the terminal value of the value function, so you can think about using that to enforce it at the terminal time and state. You can also go further. If your G is differentiable, you can also think about using like a Sobolev norm and make the grad phi also match. Okay. The really key part is actually how you evolve the state. So if you look at the ODE constraint here, I would even call like the second and the third component not really being an ODE, because the right-hand side doesn't depend on L and CJ. It's just accumulating. It's some integration that's happening. But the Z is really the crucial part. And what you can see here is that what we follow is gradient of the Hamiltonian with respect to P, which is a dual variable, basically the grad phi. And what that tells you is that basically we're using the feedback form. Another way to write this is that we use our F, our dynamics, and we plug in the U star that we computed previously. So this means now something interesting, namely you optimize over theta, but the theta also drives the sampling of the state. And the sampling of the state, of course, drives also how you measure your objective function. So this is sort of a problem. If anyone has worked on reinforcement learning in this room, that is kind of similar structure there, that you have the exploration and then the exploitation at the same time. Okay. But anyway, so this is a training problem we set for ourselves to solve. A few things when you start now about implementing neural networks for this is that you want to, for example, think about having a functional process. So what could phi be? So phi needs to be a function in space and time and space. S is time, Z is space. And it's supposed to be real valued because it's a value function. And here now you see that basically the more interesting stuff is actually driven by the derivatives of it. So the gradient and the time derivative. So you want to think about that once you design your network. Also think a little bit about the regularity of HJBs. And here is basically a relatively simple network where it has a few different blocks here. So we have basically a quadratic term that you're welcome to ignore because it's not a neural network, and I promised you neural networks. But I like adding some simple linear part or quadratic part to the model, because then you have linearity with respect to the weights is a pretty cool thing for optimization. It doesn't really hurt you to add it, so I always like to have it here. But the real meat is the first part, which is basically a neural network, and you can think about any neural network you like, that is then projected down to a scalar by this vector W. And I should say what's trainable is the W, the thetas, the A, the C, the B. Everything is just lumped into a big vector, and we call that theta as our joker. So we don't want to mess with that. In our case today, the network here is just a ResNet. Typically, it's a very shallow one. And you see the forward propagation here. What's more interesting then, once you write this down, is you want to think about the backward pass. So of course, you can use automatic differentiation these days, but sometimes it's actually also a good exercise to do this by hand. I don't think I want to torture anyone today with this, but when you do this by hand, you realize that a few things happen. So you see, for example, that this activation function, if you make certain choices, like a very popular choice these days is a ReLU. So then you get a sigma prime here, which is a piecewise. So ReLU is basically the max x,0 function. You sometimes have an optimization also. Then this would be constant. So if you are in a stochastic problem, you actually need Hessians of phi, and they would all be zeros. So that may not be the best way to go here. So you want to think about these things and make sure that it's sufficiently smooth and interesting. So again, what you really need here is also the gradient and the Laplacian, say, of phi, or even just a full Hessian. So we've done quite a lot of work that is not using automatic differentiation for these things. Because what we found is that with automatic differentiation, I mean, it's very convenient, but it is limiting yourself to matrix vector products, basically. So if you wanted to, for example, compute a Laplacian, the way I think to do it in automatic differentiation is to take all the standard basis vectors and do matrix vector products with the Hessian. Each of them would be one backpropagation through the whole network, or forward propagation, depends how you code this. And you need to do this d times if d is your dimension. And that is actually pretty expensive. So we have a recent paper that makes this much simpler by just computing this damn thing, and actually computing also the full Hessian for problems of this size, because you have to realize that the sizes here are not so huge. So you see some papers use trace estimators, but then you typically lose a lot of accuracy and get a lot of noise into your optimization that I don't think is really helping you at all. Especially because D is like 100 or so. So in numerical analysis, we wouldn't use a trace estimator for a matrix that's 100 by 100. We would typically try to just compute it. So we compute these manually, and I should say, because that's oftentimes what's coming up, is that those derivatives are actually derivatives with respect to the input of the network, not with the weights. So for that, we want to use automatic differentiation, because that's going to be too messy. But for the input derivatives, we compute them manually. It's quite efficient, and most importantly, actually, it's easily parallelizable. I'm not sure I have the reference to this, but my former postdoc, Liz Newman, she's written a very nice paper, and the code, actually, the code is probably more useful than the paper, because that is a framework for computing gradients and Hessians and Laplacians of neural networks in PyTorch, with now almost no coding overhead for you. It was quite a big achievement for us, and she did a lot of nice work on this to make it really convenient. But anyway, that if you want to use this, if you solve any neural network problems with PDEs, ping me, because I can point you to that reference, and maybe it'll be useful for you. It's very efficient on a GPU for sure. Okay. So here's maybe an example also to explain like where we would sample. So here's I call this my COVID example. So you have actually you only have two players, like an orange and a blue player. They want to pass through this corridor. So these bright stuff are walls. They want to pass through the corridor, reach their target. So they need to, and then they don't want to bump into one another. They want to kind of have like a social distance of a few feet. So that's the example. You see nicely the solution here on the right. So at the beginning, really, our network is more or less poking around. And of course, with especially with this quadratic term, it comes in handy because you can guide the sampling a little bit toward the target quite easily. But in this case, you see that, I mean, some of them are bumping into the wall. Clearly, they are overlapping, so they're violating all those constraints. But then once you have trained, you see that both, I mean, the trajectories seem to be more reasonable. I mean, the orange one makes it over there, blue one makes it over there. But more importantly, I mean, you've basically discovered which part of the state space to learn. And then we are in the exploitation phase, where along those points here, we're going to try to solve the HJB, but not so much so on other ones. So it's like bootstrapping and reinforcement learning, I think is the term. But the challenge really is you need to do both things at the same time. So you need to find phi and the relative regions of the state space. So here's an interesting experiment I asked my former student Derek to do then. So once he's trained this, and you saw where we sampled, at some point, like just make them leave the trajectory. Most of the time, not always, of course, probably, but most of the time, actually, we saw that you can sort of recover from it if the network is trained. And I should say that, you know, this could almost be live. I mean, like here, you don't, once you go to this state here, you don't solve an optimization problem again. You just get the policy from the network and you blindly follow it. The reason I should stress that is because if you actually had access to a nonlinear optimization method at that point, and you would solve the problem optimally from here, you would actually find that you could go around that wall. But that's a suboptimality of a few %. So this one is, I think, good to go. So we would take that. This is only a 4-dimensional state space. We have a higher dimensional one. So this is an example motivated by quadcopters and a swarm of quadcopters that want to go around a building and not bump into one another. And these plots are just super confusing, but nice to look at. but basically they all make it to their targets and they don't bump into one another. So this is like a 150 dimensional HJB equation, if you want to think about it that way. So 50 agents, 3 degrees of freedom. And yeah, it took about an hour back then on the GPU. Now, of course, this is like 2 years ago, so we should rerun this, and maybe the number would drop because the GPUs got better or whatever else happened. But those are sort of some examples of the deterministic problem. Don't see any questions. But, if there are, you can always chat me up, and we're doing well on time, so we can always chat about these things. So next, I want to talk a bit about stochastic control. So pretty much, I think that is the new name of the game in some sense. So it's a very innocent change. I mean, you add some Brownian motion to your dynamics. But then what happens is actually that the HJB, in this case, if you pick a Gaussian here, becomes gets an elliptic operator in here. So this Laplacian wasn't there before. I'm glad we already talked about the network, so don't worry about computing this stuff. But now what you have is sort of a semi-linear elliptic PDE. So you have a Laplacian here, and then you have some nonlinear part typically coming from the Hamiltonian. Okay, and if you open up the can of worms of how you can solve this thing, basically it's small dimensions, piece of cake probably for you guys. For me, not so much, but you can basically mesh the thing and do some PD simulations. One of our current postdocs, Dipanshu Verma, he's actually done this now with Phoenix, so I'm going to use that to compare our results against in a little bit. But that's in small dimensions, and once you go to high dimensions, this problem becomes really interesting and challenging. There have been actually quite some impactful works recently, or maybe not so recently anymore, like 4 years ago or so, where it was proposed to use a neural network for the gradient of the value function, or for the network, or for the value function itself, and then go to a framework called forward-backward stochastic differential equations. So that's a really neat framework, and it's sort of kind of cool in the sense that it allows you to solve really high-dimensional PDEs if you can solve stochastic differential equations. So that's a catch. So we're gonna look a little bit into those works. And then the key part that I want to present that is maybe novel or new for us at least is, so you can go to forward-backward SDEs, you can represent things by neural networks, so you may think everything has been done. But what I really want to stress is that you really want to think about the forward SDE here and how you design it. I think the only way we got success in the deterministic problem that I just talked to you about was because we used the feedback form from optimal control theory, which, if you think about it, is basically thinking about along characteristic lines of the HJB equations. This HJB equation does not have characteristics, of course, because there's an elliptic operator in there, but you can cook this into the SDE so that at least when the noise goes to 0, you recover the old approach that has been working for us. So that's sort of the idea, and I'll walk you through that. And then the goal is really to learn the value function, not just at a particular point, but hopefully around that point also. Okay, so a couple of goals. So here's again the framework. It looks probably very similar to what I just presented to you. I think the notable change is that now the dynamics have a sigma dW. So this is the same sampling pattern that we have. Otherwise, the rest is pretty much unchanged. There are some HJB penalties, you can call them temporal differences if you like. But the really crucial and very small, tiny looking change that we have done here is the design of the dynamics for Z. Because when you look into the literature, the papers we've been studying basically don't have this drift term. If you don't have this drift term, basically you have purely random exploration. And that I don't think would have worked for us in the deterministic case. So I don't think it would work for us very well in the stochastic case. So that's what I want to kind of want to stress, because also what I like to have is I want to generalize the other approach. So when drift term. If you are familiar with forward-backward SDEs, then you realize that actually the choice of the forward SDE is almost arbitrary, which is sort of cool, actually, if you think about it. In forward-backward SDEs, there are more choices that you can have. So we want to make the choice that is basically following the feedback form. Okay, let's see what happens. So here is a very innocent looking problem. Always like to start very simple. So this is, you have a blue point, that's where you start from. You have a red point, that's your target. And think about this bright spot here as a hill. So you want to kind of, and you're not a hiker. I know maybe in Norway people want to go on top of the hill. Maybe we should change the problem for you guys. But you know, I'm a Northern German. I'm used to flat surfaces, so I want to go around the hill because that's conserving some energy. Okay, but I want to make it to the target because that's where my dinner is at, and you know, then I would maybe want to brag about going over the mountain. Okay, so that's the name of the game. Okay, so if you try to do this, so this is a nice problem because it's like two-dimensional state space, some finite time. The solution here is actually we got this very similar solution now with Phoenix. Just didn't have the time to plot it yet. So you can consider this as sort of be the baseline solution. So you see the value function. So clearly, the farther away, the brighter everything gets, which means higher values, so more cost to go. You see sort of on this diagonal is sort of where you can decide. I mean, do you go left or right? That doesn't matter too much. You see this also in the policy here. So this is the optimal policy that we can plot. So you can do nice plotting and get quite a lot of insight actually also for these small problems. Okay, I should say we were not able to solve this with the methods that we found online. So I mean, these groups have done a nice job in putting out their code. So we've been trying to mimic what they've done and apply to this problem, and we failed. And I think the reason we failed is because in their approaches, the sampling is done with a purely random noise. So here, basically, you only stay close to where you are, and you never discover that there is a target. Whereas for us, I mean, here's just one batch of samples. We can of course also go the other way around. We actually have a feedback form that is driving the whole samples. So that's one of the insights that we had here, which is sort of interesting from our point of view, because this basically means that if I think you have interesting problems in high dimensional control where basically your control needs to make the states move, then I think it's much better for us to add the drift term here. We've also, so this is the comparison to Phoenix. So here I should say, so what you see is actually important to explain a little bit. And I'm not sure we've done the best of the best in terms of how to solve this HJB equation. This, again, is a semi-linear elliptic PDE, goes backward in time. So what we've done is we picked a large enough domain so that everything that we think is relevant is covered. We used Neumann boundary conditions on the value function, because what other boundary conditions could you think of? I don't know. Then we used an implicit Euler with a very small time step, made sure we have enough mesh points in the map. We really didn't try to make this efficient, but just to make it super accurate. And we increased all the sizes so that we didn't see any changes in the solution anymore. So we hope to have solved this problem in Phoenix. So then what you can do is you can ask yourself, so for our network, would predict the value at every s, z, and you can look at errors. What I'm plotting here is a scatter plot of the values. The top row, sorry for the small caption, so the top row is the value function that we predict, and the bottom row is basically the Phoenix solution evaluated at those points. Why do I pick those points? Is because these are the points that we would sample in the training. I told you that we have a semi-global approach. So basically at those points, my hope would be that we train this with good enough accuracy. One thing we're still trying to find out. So, I mean, it's great news, I think, at t equal to 0, sorry, at the initial time, which is here. So there we get actually pretty decent rates of the value functions. The error sort of increases, actually, at least the relative error. I mean, absolute errors are not so big because, I mean, if you look at these pictures, they almost look the same. But there are some really tiny values that I think we're struggling to get really right. But we have a 10% relative error. I mean, okay, it is what it is. I mean, the other methods just didn't work at all. So I'll take that. But that's sort of one way I think is how you can compare results to actually state-of-the-art finite element methods for these small problems. So it gives you a feeling that, and it could be that we can improve this by training differently, because we sample always at time 0, so we may be biased towards that. But yeah, I think this was a pretty good result for us to see. So and here you can actually see. So I didn't update the video before, but you can go around the hill in both ways. So the samples are almost symmetrical, which makes sense in this problem. Okay, great. So that's a 2D problem. That's not really what we're in for. This method is not meant to be for 2D, but we like it for visualization. So here is some things we've done to also see other benefits. So we basically looked at one of the example from these two papers, because they both work on the same benchmark problems. We said, okay, let's try that too. So this is a 100-dimensional HJB with a ground truth solution. So here, you set up the problem in a certain way. You get exactly the form that we need. And you have a solution to compare to. So you have a blue is a learned one, and then and the red dashed is the exact one. And like a minor improvement by the way we sample on this problem, but not so much. It's not groundbreakingly different from the existing methods. So we ask ourselves, so why would that be? And we looked at the problem definition. Because when you look at the problem definition, you see that the terminal cost here is basically having a minimizer at basically the origin. So this means that you don't really want to move, because it just so happens that the problem is also initialized at the origin. So you sample points around the origin. Basically, if you think there is no noise, the optimal control would be just to stay there. So that's sort of one thing we were curious. So what happens now is we change the problem. So we change the terminal cost so that we have some target state. So before it was just 0. You didn't see it. Now we pick an arbitrary point, like a vector of all 3s for whatever reason. And then you see interesting things happen. Namely, so here's just see some training iterations and some of the objective function. And here objective function means the control objective function sampled over many realizations. And then you can see that the existing methods for semi-linear elliptic PDEs really break down. And I should give them a lot of credit, because they target a wider area of PDEs. So it's not like we only work on control problems. Those semi-linear elliptic solvers, I think, are also interesting for other PDEs, like Allen-Kahan equations and so on. So it's and there you don't have these nice motivation for a drift term than we see here. But anyway, so that's what we have. So we could still solve this problem relatively well. We don't see much sensitivity to changing this terminal cost, but I think we have a bit more generality here. Okay. So that's about stuff that's actually currently really happening. So this, I have the reference for the paper later. We're just putting final touches on it, and then it'll be sent. So what are some possible extensions that I think could be interesting? I think one thing that is sort of hanging, is like a cloud hanging over us all the time, is how does what we do differ or compare to reinforcement learning? And of course, if you have followed any news in the last couple of years, reinforcement learning sort of seems to be the best thing since sliced bread. It's an alternative way, of course, for stochastic control problems and many other problems like AlphaGo and protein folding and all of these things. So there's a lot of excitement about this technology. And it has been for many decades the focus of optimal control and optimization people. So here, one example I think that is very closely related to what we do is actor-critic approaches. And actor-critic approaches, you have two typically neural networks these days. One is the actor that proposes an action to take, and then a critic that sort of tries to estimate the value. In our framework, the critic would be phi, and the actor would actually be the feedback form. So that's one way to think about it. And then you train these two networks. Interestingly, in RL, they don't know about one another, more or less, so they don't have a feedback form to connect them. but you can train them. And the benefit is you don't need to know any of the PDE, because here there was a lot of calculus I hit from you today. Yeah, you only need observations. So you don't even know the objective function if you don't want to. You just observe what happens and how the state changes, how rewards are collected. And so I think it is an attractive way to think about for really complex problems. Say you don't have the physics at all, you just have to deal with data and optimize based on that, then it's a good thing. Although a big challenge I see in problems that I'm interested in, which are more from scientific, like energy applications and so on, is this is not an Atari game. So Atari games, I think, you can run them very efficiently and let the computer play hundreds of hours within a few minutes. Here, if you want to actually have a good fine scale simulation, then you definitely are bound by sample efficiency. So you want to overcome that if you want to apply reinforcement learning. So what I'm really hoping to do is to combine this with the HJB equations, because I would argue that in most scientific applications, at least we know the objective function. So that should give us some benefits. And then you can think about trying to learn ODEs, which has been a big topic of our research and other researches over the last couple of years, and cook that into this framework. But I think that's sort of a good way to go for me, because I don't want to learn the objective function if someone can give it to me. If I can make some assumptions about the model, I'll take them and then start to learn from there to really guide the sampling and cut down on the number of samples that you need. But it sort of, and we have been doing a lot of comparisons now these days between reinforcement learning and our approaches, with results you may expect. So you can solve the problem typically in both ways. Both of them are going to be suboptimal compared to like real solutions, which we always like to compare to in our papers. But if you ever have trained a reinforcement learning algorithm, you realize there's a big sensitivity to hyperparameters. And I think our approach is typically a little bit easier to use once you have done all the math. So anyway, so that's definitely one of the focus areas for us to really suss out the differences a little bit more. Another thing I found interesting recently, which is not related to my prior work, is actually HJBs arise in all sorts of places, even some unexpected ones. So one is in global optimization. So if you want to think about minimizing a function, say f, you see the blue one here, very non-convex. Then one thing that is attractive to do in principle, but hard to make work, is you compute the Moreau envelope. So you have some time that smoothes out the function, and you see one particular one here. And then you do a gradient descent on the Moreau envelope and have a smart way to find the next time step. Great idea. I think it's definitely not so new. But the question is, how can you do this in high dimensional spaces? So when y here is high dimensional. That's the hard part. How do you get the Moreau envelope? How do you get the derivative of that? There are some relation to HJBs, because it's been recently observed by this very nice paper, that U solves a Burgers type HJB, so one that pretty much we've seen before here. And that means, so if you could solve that very well, then you would be in good shape. Of course, it's a difficult problem, and you don't want to replace one difficult problem with another one. So what you can do is you can actually turn this Burgers type HJBs are special, because you can reparameterize it to become like a heat equation. So you add some viscosity, apply some transforms, and then you realize that what you need to estimate for this method to work is the gradient of the log of some solution to a heat equation, which is super interesting, because then this one, potentially you can get it cheaply in low dimensions. That's what this paper is about. For high dimensions, it's more of an open problem how to do this. But this term is exactly also what you need in what's now known as score-based diffusion models for generators. So there's a lot of link to machine learning applications. This is one other excited area, I think, that we're looking into. And yeah, if I want to wrap up, so should always leave you with a few properties here. So really, if you want to think about what we've been doing for the last hour, is we use neural networks as function approximators. leverage maybe some of the advantages in machine learning and optimization for getting these value functions. I'm definitely not tied to neural networks. So, I don't want to sell you this as a big magic deep learning type of thing. It's really just using their ability to approximate high dimensional functions very well. If you have another high dimensional function approximator, this you can plug it in. What was really key for us is to use some of the math here. So the PMP to guide the sampling, the HJB to penalize the loss function, and then Lagrangian PDE solvers for the HJB. Yeah, hopefully I showed you some promising results. Other areas I think I should mention we have worked on in the past were mean field games. Similar idea, and optimal transport actually is a specific part of a mean field game in our notation. It's a bit more complicated because you also have to estimate some densities of a distribution, but that's okay. That's actually, we started with that one. So we have a paper on that too. If you can't find it, email me. Currently, we look at PDE control. So that's infinite dimensional HJBs, definitely comparison to reinforcement learning, score-based diffusion. And I always like to list also some limitations, or I would call them opportunities for people to work on. So definitely, one limitation is, we can only get you semi-global solutions. So if you find a better way to make it more global or even completely global, I think you're in good shape. That's a good idea to do, both in theory actually and in practice. Should say we don't have any convergence results. So we pick a network, then we train it and see how it goes. It's also there that you can use to automate this process. But it is not very satisfying. I would really like to have convergence without like a finite element method. If you have one, send it to me. And yeah, of course, training neural networks is not the easiest thing. There have been many ways to make it work, but it's not as straightforward as solving a sparse linear system, which I would do any given day. But yeah, if you can do it. Cool. With that, probably I'm going to stop, and maybe we have some time for questions and ideas and feedback, and you can grill me with tough questions. That will be awesome.
Thank you very much for this very nice talk, Lars. Are there any questions in the room or also online? I think if you're online, you maybe have to unmute yourself and just ask the question in the chat.
I have a question. Sorry.
Yeah.
Thanks for the talk. Could you please lose some words on how to link optimal transport problems to this machine learning approach?
Yeah, so a whole other talk. I think I can find it on YouTube for you if you email me. But pretty much, okay. So how can we model optimal transport? Is we model it as a mean field game. So we think about this as a, dynamic optimal transport, Benham-Rupert-Bernier stuff. So you basically have a PDE constraint that's a continuity equation. They set it up as a boundary value problem. So you have a row 0 as your initial density, row 1 is your target density. You relax that to make it a terminal cost. And then what you have is everything is governed by the value function. So the value function it depends now on the row implicitly. The gradient of it tells you how everything is moving. Mm-hmm. And then the key is you eliminate the PDE constraint, which is the continuity equation, with a Lagrangian solver. So you take a Lagrangian method, and along each trajectory, you can actually do the density estimation efficiently.
Okay.
Yeah, very, very, very short description, but I can send you for sure a paper. And I can also send you the talk. If you cannot find it, then just email me.
Okay, yeah, would be great. Thanks.
I can actually drop the paper here in the chat. That's
perfect.
That's an excellent question. It's not. Thomas has a question. Which convergence results are missing exactly? Oh, that's a great question. So this is becoming more to my wish list type of thing. So what I like about finite element methods is that if I double the degrees of freedom, my error will go down in a certain way. And if I keep doing this, at some point, this method should converge. So nothing should change anymore in my estimate. For a neural network, not so much the case if you've ever worked on this. So you can think about, okay, so first you need to say, so what is the parameters here? So parameters could be the weight matrices you have in your affine layers. And you can always think, and in theory that's true, so you can give it more neurons, which is making the matrix bigger, gives you more weights, gives you more expressive power, and you can do everything. But the optimization problem is really hard for neural networks, or can be hard sometimes. So if you say you have trained your network with a width of 32 neurons, and now you go to 64 neurons, all bets are off how this is going to behave, I think. So what I would love to see is some way, and I think it ties, it's not just a theory work, it needs to be tied together with the practice of the optimization also. So finding a way that actually works so that you can train a small network, make it bigger, not lose everything you've learned, and then just improve. And then you would want to show that this converges. So that will be my wish list. Every day I come to work, I have this wish that someone figures this out. And but yeah, it's not an exact, maybe not exactly enough for you, Thomas. But that's part. So what I would really want to have, like basically a guarantee that with a bigger network you can sort of bound the optimization error and improve. Okay, Thomas will write to me later. Happy to hear. Okay, Christina has a question, I think. You're mute. You're on mute.
Yes,
so.
Yes. Actually, I actually have. Yeah, I'm with Christina. I'm a colleague. Thank you very much for the talk, because it was very, very exciting. I have a couple of questions. The
Sure.
first one is, how did you impose the state constraints? For instance, in the picture that is displayed also here, I guess that you used a soft constraint, right?
Yes.
Okay.
And that should also be part of my wish list. So
okay.
Here, basically this constraint of them not bumping into one another. The only reason I could implement, or the only way I can implement this, is by doing a soft constraint. Basically, it adds a lot of convexity and a lot of stiffness and a lot of problems. But basically, when they come too close, then you get a huge force. The challenge here that I think that's another thing for my wish list in more general terms. How do you have state constraint in a stochastic program?
Okay.
That, I think, is always tricky for me, because I cannot do Lagrange multipliers, because then I sample a new batch, and what do I know? I could set it up maybe as a game, like a GAN type thing, but then I don't want to really mess with GANs and GAN training, and it's also hard. So if you have a better way to do that, that would be amazing. But the challenge for me is that it's a stochastic program, and they're having state constraints.
Actually, we are dealing with the deterministic state constraints. So we are.
It's a deterministic state constraint, but you're going to resample the states. So, like if you have one batch and you can monitor your constraint, and you can get Lagrange multipliers, whatever you can get. But then you have to acknowledge that you resample, and then all bets are off typically. So that's a struggle I have, because of course you can do what I would call sample average approximation. So you get a big batch of samples, and then you treat it as a deterministic problem. Then you can do everything you want. But most of the times these problems are stochastic, and if you ignore it, then oftentimes you don't generalize so well.
Okay.
But yeah, if you have anything along those lines, I would be really happy to reading that.
And the second question, if I can,
sure.
Regards something that you mentioned, for instance, in slide 5, the course of dimensionality. So
yeah.
If I got correctly your point, so your basically your competitor is the finite element approach, right? So
only in small dimensions, like dimension 3, 4. I think we can.
Let me say in dimension 100, let me say competitor is the finite element approach, and the course of dimensionality of the finite element approach is that essentially the number of degrees of freedom scales exponentially with respect to the dimension if you keep fixed the diameter, right?
Okay. Yeah, in 100 dimensions, I don't know of a Sorry, I think my connection was wrong. So in 100 dimensions, I don't know of any competitor.
Okay.
You cannot use Phoenix for that. If you look at the documentation, it stops at d equal to 3.
Okay, but what was more or less a philosophical competitor, not a practice.
Yeah. So but I think it's still important actually. Not sometimes when I read stuff, you always want to, even when solve the biggest problem you can solve with a good, provably convergent scientific computing tool, and compare your neural network to that. Because we can't just wave our hands to say, we only look at 100 dimensions. So there we had an analytical solution, which is also a good way to compare. Yeah, so that's why I always like to have these small problems, because that's one problem we can solve in Phoenix. We can set it up. We know the ground truth, and we know where we stand, and then people can see if it's good enough for their application.
Okay. And what I wanted to ask is basically in your case, you don't have this scale, you don't have to construct a mesh, but on the other hand, you have to sample from that probability measure row. And basically my question is this probability measure row, how is done the support of this probability measure row? Usually, let me say thin with respect to the huge dimension. This is the core of my.
So what we did in our experiments, I think it's a more application question. Like, you pick the row that the application would give you. So what we did is we just put the Gaussian around an initial state.
Okay.
So that's hopefully giving us, some way to generalize to nearby points, but not completely far off.
So in huge dimension, this would be quite sparse. It would be quite a quite sparse picture, right?
Yeah. So if you, it's a great point, because it's also related to something we're doing now. Is of course, if you now think about PDE control, PDE applications, then you know that this is not a good way to do this, because basically, if you take a univariate Gaussian and increase the dimension and number of grid points, if you wish, to infinity. This is not going to give you any well-posed measure by any means. So there you need to have different types of measures. So you want to be careful. Here the dimension today was large but finite.
Okay.
There using a Gaussian is okay.
Okay. Thank you so much.
Yeah, thank you. They were excellent questions.
Are there further questions online or here in the room? I have maybe one. So
Sure.
Like you said that you're not tied to neural networks as function approximators, like also a bit related to Carl Kunish's talk a few weeks ago. What other function approximators are you thinking of? Is it like mesh-free methods in general?
You tell me. I just want to emphasize, that, with all the hype going on, I think for these problems, neural networks are the best I can find. But there may be other people having other ideas. There are some works, I think, on tensor trains, or at least, up until maybe 10 dimensions or so. Sparse grid, I think, are also great. I used to like those. They typically don't also go beyond 10 dimensions. But yeah, anything whoever knows which will pop up. Especially since this is on YouTube, I want to make this talk relevant even maybe a week from now when someone comes up with a better model. But yeah, I don't have a good idea. Like for 100 dimensions, I don't have a great idea, because of Gaussian processes, I don't think scale so well to that dimensions. And neural networks, with all the difficulties that you may find and with all the messiness going on, we can make these work. It's not maybe the most the easiest process, but there have been many advances that you cannot deny. If you think about AlphaGo or AlphaFold, these networks have been trained to solve really difficult problems on a conceptual level. These are infinite dimensional HJB equations. Like, of course, they don't see the HJB equation because they don't look at it, but they are getting apparently practically meaningful solutions to that. So,
yeah, thank you. Like Thomas has one question more, I guess.
Oh yeah.
The last question for this talk. It's in regards to sampling. Have you thought about using something quasi-Monte Carlo or randomized quasi-Monte Carlo to maybe get a better covering of the state space?
No, but we probably should.
Cool.
Yeah, I've looked into this at some point, Thomas. I was interested, but I haven't had time to really do it. Yeah, I think it would be better. Anything you can do. You can also probably mix it with some random exploration. Anything like that would be interesting.
So thank you once again.
Yeah, thank you guys.